So thank you, Chairman, for your nice presentation, and thank you everyone for being here. Today, I'm going to present you a solution for structural health monitoring. I will start from the scenario and I will introduce the application. Imagine you have a structure, like for example, a bridge. If you look in the literature, you can see that a good solution just to have information about the health status of your structures is to deploy vibration sensors all around the structure. Then you can collect data from all those sensors and send the information to an aggregation unit. This unit will perform an inference about the health status of your structure by saying if it is healthy or not. And nowadays, you can do that, for example, with the automatic algorithms like machine learning based, for example, random forest, deep learning, and other solutions. One of the main limitations of these approaches is that if you want to collect a lot of data and send them to the aggregation unit, you spend a lot of energy by doing the transmission. So you can see in the literature that there are a lot of approaches that tries to compress this information. So in practice, you start from the sensing node, that is a node that is supplied by a battery, and you want to spend the least energy, the least possible energy in this sensing node. You want to compress the information, send the compressed information to the aggregation unit, reconstruct. Here you want to reconstruct the original data and then do the inference. In order to do compressions, has been developed in the literature the so-called compressed sensing paradigms. In practice, we project our data in a new space with m dimensions, where m is much smaller than n, that is the number of samples that we collected for the original data, with a simple matrix multiplication. The key point here is to retrieve a good compression matrix. And there are a lot of approaches in the literature that does this function. But the key point is that even if you compress your data, you have to send a lot of compressed coefficient in order to reconstruct the data. In this work, instead, we try a little bit a different approach. We decided to avoid reconstruction. The idea is very simple. If the compressed coefficient contains all the information about the original data, then the machine learning algorithm can use the information in this domain. It is not so easy to be interpreted by a human user, but the amount of information is the same. In this way, we can test another thing. We can try to compress more. I mean, we cannot reconstruct the original data, but if you are good enough in maintaining the important information, we can classify the data correctly, even sending less information. This is the key point of this work. And this allowed us to do another step. If we want to do the classification in the compressed domain directly, we can extract the feature directly in the sensing node. Of course, we cannot reconstruct anymore. We lose this capability, but we send much less data. In fact, we can extract F feature, for example, that is much, much smaller than M. And so the energy to transmit those data is much smaller. Of course, we pay more computations on the sensing node. For the feature extraction, we selected the feature set that is from the literature, and it is efficient for the implementation on embedded systems. Those are 14 features that measure statistics about the coefficients, but I don't want to enter into the detail of this part. If you are interested, you can check on the paper. Let me validate the proposal. I will show you two things. I will show you that we can maintain a decent accuracy comparable with the existing methods, and that we can spend less energy. So I will show you two experiments. We used real-world data. we use the data from a real-world bridge from the Switzerland Highway that has been dismissed in 1999, and it has been manually damaged for 1 year. So we have data of the healthy status and from in the damaged status. And we have around 5,000 data. Let me go to the experimental setting. For the compression, we use the model from the literature that is somehow state of the art. It's a compression model that has very good performances against the noise and that allows good level of compression, even when you want to reconstruct your data. But we will compress more, a little bit more, a lot more. For the classification, we used random forest. Why random forest? Because it's a good solution. But of course, you can try different models. This is not the point. I'm not presenting the random forest. I'm presenting the idea of working on the compressed domain. And for the validation, we used a standard 5-fold cross-validation that allowed us to have always a fresh test set that has not been employed for tuning any of our parameters. The results for the accuracy, let me say, for the generalization performance are here. The table seems huge, but it is not. Let me explain it. The first two rows are the classifier and the compression rate. This group that I show you here is our proposal. As you can see, we have the random forest for the classification, and we used a lot of compression levels from 4 to 256. And these compression levels are much higher than the ones that you can find in the literature. In fact, here we have two recent baselines, 3 recent baselines published in 2 recent works, that does this same thing. They try to classify the health status of our structure, but reconstructing the information in the aggregation unit. In fact, as you can see, the compression rate is much smaller. They can reach 6, because if you want to reconstruct the information, you cannot lose too much information. In this case, they were not compressing at all. Okay. This is the generalization performance of our model. We can see 4 metrics. As you can see here, we have some changes in the distributions of our labels. In fact, for example, you can see that our accuracy and our precision is a bit less than the other methods. But for example, the precision and the recall and that one are a bit better. In practice, from this kind of analysis, you can see that, okay, it's changed a bit, but it's not so huge, the difference. What is huge is here. In fact, with the previous method, you have to send all the coefficients. And so we send more than 5,000 data. Here, we send 13 features because we have only the feature set. Please pay attention. We have lost an important feature. We cannot reconstruct, I will say it 1,000 times. But for our target problem, we can achieve the same performances, spending less energy. As I said at the beginning, we are doing feature extraction on the sensing node. So we should test that in order to extract our feature set, we don't spend more energy. So let's test it. We have our simulation. We considered collecting data, 1 sample each hour. That was the original sampling rate of the problem. So we do the inference 1 time every hour. This is reasonable because structures changes their status very slowly. We considered our sensing node supplied by a battery with a standard capacity and with an average reference voltage. And we consider to equip a low-end microprocessor that has a working frequency of 80 megahertz with standard current consumptions. Okay, this is our setup. Here again, the results seems difficult, but it is not. Let me explain all the points. Here we have our compression rates. So here there are the compression rates. Please remember that if you want to reconstruct your data, you should stay here 20 is too big to reconstruct your data. We should stay here. Here on the axis, we have a ratio between the energy of the reference works from the literature and our solution. So every time that we have a value that is higher than 1, we are gaining lifetime for our battery. We are spending less energy. Greater than 1 is good in our plot. The energy is measured as the summation of 3 factors. The energy for sensing, the energy that we use to collect the data. The energy for idle state, when our system is doing nothing. That is most of the time in a system like that. And the energy for feature extraction, compression, and transmission, the 3 most important factors. We considered 3 transmission protocols. Everyone is Wi-Fi because, of course, we cannot connect with wires, sensors on a bridge. Okay, so we have 2 comparisons from the literature. The first solution that does not compress the data at all, that is shown in the upper part with the yellow background, and the solution that uses the compressed sensing. That is the one with this, I think it's gray background. So the 2 methods that we compared here, these 2 references. As you can see, if you do not do compression, you pay a lot of energy. In fact, in the worst case, our gain in terms of energy is higher than 10 at 2. So we gain a lot of energy. But this is reasonable because we have to transmit a lot of coefficients. And in fact, the transmission with protocols that are much long range is more energy demanding. Here we have the compression, the comparison with the compressed sensing solution. As you can see, if the compression becomes very high, the gain is smaller. It is always greater than 1, but it becomes smaller. But again, paying attention that if you want to use the previous methods, you should stay here. And so your gain is always close to 10 at 2. With this, I concluded my presentation. Thank you for your attention.